Thank you. Hello, everyone. Thanks for being here for this lecture. So we will continue, and today we can finally see some links between what I presented before, like circles as weighted points and all these structures that we can define thanks to them to other patterns that you know maybe better, like circle packing. And I should mention that this will be a very discrete setting and viewpoint that we will have. And for this, I will start with very short reminders in terms of the definitions to be self-contained in this lecture. So Voronoi diagram of a set of point set, again, it will be defined in any dimension in our D, but here we are more interested in 2D setting, like mainly triangle meshes, as you will see, either on the plane or surfacic one, so triangle surface meshes. So my main focus will be in 2D, but these basic definitions are perfectly generalizable. So you know the triangulation in the context of Euclidean distance. You have a 2D example here, given a finite point set. You can define the partition of the space based on the Euclidean distance that would assign to each of these points the set of closest point to this one. And that would separate, indeed, each pair of points by a bisector. That would be perfectly easily definable, and that would give you these convex cells that are somehow dual to the points that you have you had it at the beginning. And the dual structure in this setting would be the so-called Delaunay triangulation. So you will define it as the nerve of this diagram that you have seen, and that it's well known that in generic position, if you are not in the generator situation configurations, that is a triangulation. It's a spatial complex here. Indeed, it's a Delaunay triangulation here, and it's a canonical. About the complexity that we mentioned last time. Now I'm sure of the exact function for high dimensional spaces. The complexity of the computation of this complex in RD, if you have endpoints, that would be of order of big O of n to the power of a function of d, and that was the thing that I was not sure of. It's the floor of d plus 1 over 2. Concretely, in 2D mainly, that would be much more simple. It's on n log n. With randomized algorithms, we can have it in n log n with n log n complexity. And in terms of 3D Delaunay triangulation, that would be okay, so we are interested in circles as weighted points, and I will just define and remind the definition of power of a point with respect to a circle. So given a circle, the power of this point P with respect to the circle would be simply just the distance pt, the tangent length that you can see there. That would be the same thing as Pm times Pn, so nothing really particular here, but the interesting point is that based on this distance, you can slightly change the definition of your Voronoi tessellation in order to have rather the usual bisectors, Euclidean bisectors, the power bisectors that would separate your pairs of circles this way. So that if they are intersecting each other, that would be really the intersecting, let's say, bisector. They can be perfectly disjoint, and you will still have a position for this bisector that would be linked to the difference between the two weights, if you want. And here, by the weights, I mean the square of the radii. In general, it doesn't need to be positive, but if you want to illustrate it here, these are positive. Based on these bisectors, you can also define the nerve, just the partitioning, the Voronoi, generalized Voronoi diagram that is also known as Laguerre diagram or power diagram, and the corresponding nerve also would be a generalization of Delaunay triangulation that we call weighted Delaunay triangulation. We also talked about the equivalent definition, regular triangulation, and why they are interesting. I would like to come back to this orthogonal duality because it's very interesting in our context. Indeed, by doing this weighted circle consideration, you can really play with these weights in order to span the whole space of, you can have this dual point anywhere on the triangle, right? So by just playing with the weights. So this is a very interesting property, and also another property in terms of the duality of these things. I'm so sorry. The duality of these things is that the point E that I show here as the dual of this triangle, if you now take this tangent length that I talked about and you just draw a circle with that radius, what you will have would be a circle that is indeed perpendicular to all of the three other. This is an interesting property that we can mention. And this duality is true for any k-dimensional simplex at the end for like higher dimensional spaces. And we have seen before a kind of parametrization theorem that says that if you define a dual compatibility in the combinatorial sense, what you can show is that the pairs of dual complexes in this context would be always a perturbation of these weighted Dirac triangulation and their duals. So this is interesting for us in mesh processing because then we can just characterize them by the position of the points, a set of weights that are changing somehow independently, and then this displacement vector, okay? This is very important because I will link it to circle packing context. These two different and independent parameters are important for me to describe the link to the circle packing. So, okay, here is just a very first illustration that would give you an idea of why these patterns are linked to what we have seen. You can see that this is almost the same idea. In terms of circle packing, you always have a finite set of, at least in this context, a finite set of circles that have a specific configuration. In this case, it's a sphere packing, and you can see that they are all tangent together. So the combinatorics, that links that encodes somehow the neighborhood between these circles is important to us, and that can be encoded through the structures that we have defined. But for this, I need to introduce many other techniques and details and definitions. So here is a kind of summary. These packings, circle packings, have been studied widely in computer graphics for various applications. The basic one that we can talk about is texture mapping, and you know that they are linked to conformal geometry, conformal mappings, and these are very important for us in order to have the less distortion possible when we map a texture to a surface. From a theoretical point of view, in the discrete setting, there have been many trials and different approaches. I will try to cover some of those, mainly in terms of geometric flows, the discrete Ricci flow that was somehow considered, as well as the inversive distance packing that is highly linked to the structures weighted triangulations that I mentioned. For all of this, I would need to again come back to the two circle configurations and talk again about how we can really distinguish between different configurations. You remember this Lager geometry, this idea, which is based on the power distance that I just recalled. If you define a kind of distance between pairs of disks or circles based on the distance between their centers and the corresponding radii, so you will be able to distinguish between the case where they're like orthogonal to each other, the case where the angle is bigger than this pi over 2 angle, or smaller than 1, okay, based on the values of this. You remember, for example, the case of applications where we wanted to encode somehow the these configurations in order to have statistical signatures. For us, these kind of configurations were very important, and we had to introduce another distance that was normalizable somehow in order to have good statistical, signatures. But here, if we want to talk about circle packing, it's more the angle between circles that is interesting to us. And here is just a slight change to what we had before. And you can see that that would allow us to cover slightly more configuration, in the sense that you can now see a difference in terms of the angle in the case where they are intersecting with each other. When they are tangent to each other, that would be exactly equal to 1. And when they are disjoint, you know that the value will be bigger than 1. So you can better somehow see what's going on in terms of the two circle configuration. And it comes from the fact that given 2 points, let's say Ci, Cj, representing the centers of the two circles and the corresponding Ri, Rj as radii, the distance between the two that I will show with Lij can be written like this, as a function of this radii and the cosinus of the angle between the two circles. So, and this is exactly the reason for which this distance has been considered for circle packing, and it was introduced a long time ago, and the name that was given to it is inverse distance between circles. So here is now the complete notation that you can compare to the definition that we had before. And based on that, indeed, you can now define an encoding between a set of a discrete set of circles, if you have, to say how do they interact with each other. For example, if they intersect with each other, what's the angle between them? And if they do not, based on this inverse distance function, we can still say something. As soon as they do not, none of the centers is included in the other circle, we can define it in a proper way. I will come back to this inversive distance circle packing. I wanted just to give you an idea of what's going on and say that indeed the basic motivation for this was, of course, discrete conformal mapping. And to be, again, self-contained, I need to talk about conformality. So we all know about the conformal maps that are supposed to indeed preserve angles, probably not necessarily lengths. And in the smooth case, you know that you can just define it based on this kind of conformality equivalence to relate the Riemannian metric that you have to any other Riemannian metric which is conformally equivalent to it. And that would be just somehow the change of the metric in terms of the conformal factor that would be encoded through that. In the context setting, one of the conventions somehow to represent this kind of conformal equivalence would be through the basic metric representation that we have. Metric is supposed to give us the length. So in the discrete setting for triangle meshes, the metric is encoded by Lij, so the length of the edges. And so the equivalence would be defined as exactly in the same way, but we need to associate these conformal factors locally to vertices. It's the discrete case. So that's why we will have indeed two conformal factors associated to different vertices. Okay? So trivial definitions. And okay, the interesting thing is that, okay, we all know that based on the Poincare uniformization theorem, so for each class of conformal Riemannian metrics, we can do what we call the flattening, right? There exists a metric that would have this constant curvature. So, and this is one possible way to obtain it is through Ricci flow that was nicely studied in the continuous case. So it's supposed to conformally deform indeed your Riemannian metric to a smooth surface that would have this constant Gaussian curvature. And this curvature indeed evolves as a heat diffusion. And that would be based on that we can just ensure that the conformality is maintained. So the discrete version was also introduced, and it's based on the equivalent that I defined here, that would be just the derivative of these local conformal vectors that would be assigned, or that should be equal to the distance that I have to the target constant curvature. For example, at this vertex I, how far I am from this target constant curvature. For example, if you want to flatten a surface, triangle surface mesh, if you are on a very highly curved region, this derivative will be higher, and then you will introduce more distortion at the end of the day. And the way they do it, it's based on the gradient descent. And but I didn't say what is the discrete equivalent of curvature on triangle meshes. For the ones who don't know this definition, that would be simply indeed the angle deficit with respect to 2 pi. So why? Because it's supposed to, for example, represent the discrete Gaussian curvature. So if you are on the flat case, locally flat case, you would like it to be 0. So that should be exactly equal to 2 pi. And then you can imagine if it's for the 2 other cases, if it's hyperbolic, it should be negative and the other one positive. So this is a way to represent it. And usually for this kind of equivalence notion definition, we try to preserve some classical properties in terms of smooth setting versus discrete setting. For example, one of the good properties that is preserved through this definition is the Gauss-Bonnet theorem, which means that if you take the total curvature of this vertices, at the end of the day, that would be topological invariant entity, and that would be 2p Euler characteristic. Okay, and again, here also the idea is that even on in this, you can see this curvature as a integrated value over piecewise linear regions somehow. It's why we have a normalization here, because you are somehow assigning this curvature to the vertices. You are just compacting there, and you can see that by doing this deformation, for example, going from bunny to sphere, you're somehow canceling out its negative and positive curvature. So it's really the same spread as in the continuous setting. So I'm not probably running anything new in this context, but it's to say that it was applied by different colleagues, indeed, in our community to cortical surface analysis. And it's just to be able to somehow analyze in a better way the deformation of the cortex based on different disease progression. I mean, that can be for Alzheimer's disease, for example. These are allowing us to extract some features based on this Ricci flow-based formulation that are helpful in Alzheimer's disease classification. So mainly David Gu from, I think, Stony Brook University worked a lot on this kind of applications. Recently, we have tried to also consider the whole evolution of these conformal factor values during the Ricci flow, discrete Ricci flow procedure to use as a statistical. I will close the parenthesis here on Ricci flow. I will just mention the fact that this discrete conformal equivalences are very interesting to people in the computer graphics community, because, as I told you, we are interested in texture mapping, namely, and there are different techniques linked to surface parametrization that allowed us to know more about the equivalent of conformality in the discrete setting, and the techniques that would allow us to for example, do conformal flatting. My goal in the second part, let's say, of this lecture starting from now would be now to provide another viewpoint to this discrete conformal setting through weighted triangulations. Because as we have seen, and Lij that were linked to each other, and we tried to somehow compute using a flow the values of Uij, and then little by little converge to the metric that we were looking for. Here we are trying to somehow separate them, and this is done through circle packing toolboxes somehow. The idea is to encode this conformality of your map as the preservation of the angle between the circles. So nothing surprising, and you would allow the scale, the size of the radii of these circles to change. So that would be somehow the distortion that you are introducing. But as far as the angles are preserved, you are fine. And the angles, as we said, were nicely encoded through circle packing definition. Okay, so now you can see the exact link with weighted triangulation that we mentioned, because there, in order to encode the metric, first of all, we, as I said, for triangulation, we need to encode the metric through the edge lengths. And we need, of course, to have triangle inequality, and that would be the exact set of constraints to consider. By adding the weights to it and do some computation, you can see that the corresponding metric representation would be the following. So linking the values of Vij that are somehow the square of the radii that we have seen before to Lij. But again, the idea is to separate these two values from each other. Using this metric characters, using this representation, we provided a metric encoding indeed for weighted triangulations. So it turns out that we can cover the whole metric of these triangulations in three manners. The first one is so these are all in the discrete exterior calculus setting. We needed that. That's the language that we have used. It's why I'm using Hajdú-Star 0, etc. But it's nothing else than indeed the area of the corresponding dual in the weighted Voronoi set. And the other value that I would need would be indeed the sum of the two opposite angles to each edge. The other one is this curvature, Gaussian curvature somehow that I mentioned, and the ratio between two dual edges. And I'm more interested in the very last one that is linked to circle packing. It's the Gaussian curvature, or this deficit area, or the sum of the area, it's equivalent to that, and the inverse distance for each edge. That is indeed sufficient to encode the metric. And here is the simple equation that links them to each other. Lij can be written as a function of these weights for the two corresponding vertices, plus an expression that is again a function of them and the inverse distance. Okay, there is no magic here. You now know how we can control the conformality through this setting. We are given a set of inverse distance that will be fixed, and we will try to find the corresponding Lij and weights to verify this, given all the hard constraints that we have in terms of inequality. And the interesting fact is that these two values are now separate. It's not like in the Ricci flow. And that's the way we do it. So you can see that by doing just a change of variable, first of all, you can just retrieve a very similar expression to the expression that we had for the conformality in the discrete setting. And this is nicely, this is still more interesting because that would allow us to converge to a convex functional indeed. And this whole circle packing computation would correspond to a minimization of a circle packing energy that is indeed nothing else than a convex convex optimization. And how do we do that? We will just optimize with respect to WI and LIJ, like we will alternate, and we will end up with finding it's just a conformality condition. We want to preserve. We want to preserve this. That was the angle. If you remember, that was the cosine of the angles, right? So somehow the conformality is encoded through the prescribed value of this, and then the rest of it would be completely, relaxed and independent. We can just solve for it based on these given values. We can also retrieve, indeed, the case of tangent circles. The tangent circles would correspond to the case where this theta ij are equal to 1. As we said, the inverse distance would be exactly equal to 1. So, and also, it's easy to see that that would also correspond to the case where this red dual circle that I mentioned, which is perpendicular to all the three, is indeed the in circle. By doing that, the only energy that one can consider in this variational setting would be to minimize the distance between this dual vertex, which is the center of this red circle, and the in circle. And this is, again, we can turn it to a nice formulation that is a convex functional that we can optimize for and end up with stable and nice sphere packing in this case. This mainly this in-circle situation with tangent spheres are very interesting in architecture and freeform design, where the circles that they have are tangent to the boundary of their cells. And they have different techniques to solve for them. They have different constraints in terms of the fabrication material and also different polygonal shapes that they want to also incorporate in this model. So I cannot cover that topic. It's a whole sub-community. And I wanted to mention at least one of those beautiful papers done by some colleagues. This is very interesting. So I still have time to cover another interesting property of weighted triangulations that is somehow linked to different applications and optimal transport. But if there is any questions here, I can take them. Yes. I'm trying to link it to this kind of setting. Indeed, the fact is that somehow this conformal factor is encoded through these UIs that are linked to log of WI. And before, we were just considering them like linked to LIJ values, and we're computing each metric step by step. Now you make it completely independent from LIJ in terms of the metric characterization, and you try to preserve the conformality through this variational method by preserving the angle. And the angle can be explicitly just controlled and fixed in the optimization. That will go through the optimization, which means that you will optimize based on the values that are given. You mean for architecture? Yes, so this is they need to repeat. Exactly. That is a very particular case. Of course, they cannot cover all the. Based on this kind of constraint, they solve for different things, right? So, But again, it's a very, very particular case. Sometimes they want to fit, they have, sometimes it's a constant radius. Sometimes they have a finite set of like categories of tiles that they want, like other patterns that you know, Penrose, and they try to somehow mimic the structure based on this kind of optimization. They go through other techniques. Here, I try to like solve for inverse distance circle packing through weighted denominator. If there is no more question, I would like to explain another interesting property of weighted triangulations that I think some of you know already, that was highly applied in different domains. It's, again, this question of points, vertices, xi, and the radii that we were mentioning. The idea is that here I would consider, rather than, for example, the angles that we had, I would consider the volume of the corresponding dual cell. And that can be indeed interestingly true in higher dimensions, but again, in my setting, let's consider it in 2D. What will happen is that if you give me a set of points without the weights, but instead of the weights, you give me what I will call the capacity. The capacity would be just the volume of the dual cell somehow. Then I can always solve for WIs so that the corresponding weighted power diagram or weighted Voronoi diagram will have exactly the cells with that volume. So it's exactly this setting. If you give me a set of points and a set of prescribed like capacity volumes that can be only with constant density function, or that can also integrate a kind of density that lives on the space that I have, then we can always solve for WR such that the corresponding diagram has exactly cells that would match with this. And this is known as a capacity, constraint capacity setting. And it turns out that it can be done through a convex minimization of Dirichlet energy in this setting, which is linked to it, optimal transport reformulation that was nicely done in the literature. So it's nothing else than just minimizing this Dirichlet energy under some constraint, which is this volume constraint or capacity definition that I told you. You are given this value mi's, and you will try to make sure that the integral of the density that you have over the volume that is dual to VI to XI would be exactly this MI. By doing some Lagrange multiplier, rewriting, you will find the following energy to minimize, where the first term is exactly the energy that we had before, the Dirichlet, and then you will have indeed the Lagrange multipliers that will exactly match the WIs that you have. This is kind of interesting that it happens, and it's true. And this is something that you can easily solve for, and it has interesting applications. Why? For example, think of the example that I said I've shown here for data representation. That was maybe the most common application that they had. Imagine you have a data set for which you would like to have a partition, for example, for visualization purposes, that provides like bigger cells based on the capacity that is assigned to them. So you can always come up with a nice partition that is somehow following the prescribed capacity, and it has indeed more interesting applications that was considered in different papers in computer graphics. One of them is what is called power particles. It's to simulate indeed incompressible fluid, and it turns out that using, like representing fluid with these particles, power particles based on this capacity constraint, the formulation that we have, we can really have a quite efficient technique to compute them based on power diagrams. So this is one of the examples that I wanted to show. And I would like to come back again to 2D and show you a very tangible example where this kind of geometric control can provide interesting setting for data augmentation, art design, etc. So that's in the context of texture synthesis. There are many interesting procedural texture synthesis that allows you to generate on the fly or on GPU nice patterns and textures with some controls through, for example, in this case, Gaussian noise to somehow control the kind of pattern that they have, etc., etc. And the idea behind it is the following. Indeed, they use a kind of Gaussian noise vector that sends the coordinates to a predefined color map from which it will read the value or the color of that pixel. And these two coordinates and these two texture coordinate and the corresponding color will generate you, like pixel by pixel, the corresponding texture. So it has some interesting properties, mainly that was designed in a way that it can be computed very efficiently in real time, and you can see that it covers a good spectrum of nice textures. And I mean, no, I mean, based on the changing these two ingredients, you can nicely integrate the distance there. So this computation, this procedural computation based on micro pattern is something that can be efficiently done on GPUs, right? Because if you have bigger domains, more complex noises that you need to be able to somehow generate these things in a interactive manner, and these are interestingly done. And the fact is that although you have this kind of filtering in a very efficient way, what will happen is that you don't have that much control on the color map itself. And the geometric nature of this color map reminds you of the capacity constraint setting that I have shown, because one can take, for example, the palette of colors that was given by, let's say, by the user, and then we can think of the situation when more, let's say, control is provided to the user. For example, he or she can provide the proportion of colors that is needed for this pattern. Based on that, and probably some information about the neighborhood between the colors in the texture, we can use the same machinery to do what? To apply the same kind of optimal transport setting that was indeed used for point patterns, where the density, the function that I was talking, the rho of x in the setting, was the density coming from an image. Here, the density would come from what? The density would come from the information that is encoded through the two Gaussian noises, because the two coordinates are coming from these two noises, and you need to see for each of these colors what's the overall proportion of color that you are somehow considering based on these two noises, right? This is something that can be computed, and once you have computed that, you can indeed deduce the corresponding values, which means that you can consider the, first of all, the xi would represent colors, their position is not important, it's their cell which is important. And wi would be a weight that we will solve for, that we will optimize for. And the corresponding dual cell would be the area that would be colored in the color map that would need to verify the capacity constraint context. This is an illustration of how the interface is working.
The interface would take, for example, a set of colors and the possible connection between them. Then what we will do is to take also the proportion of colors that is needed, and by solving for the WIs that would give us the corresponding capacity for each of the dual cells, we will compute a color map whose final result would match exactly the proportions that we have set, knowing that the density function comes from the two Gaussian noises that we have. We can also explore the space of Gaussian noises by just playing with the frequency spread, the orientation, in order to change the style of the texture. So this is a space that we know much less about. We are trying to characterize that as well in order to have a kind of nice classification of the patterns that we can have. But at least in terms of color proportion, it allows us to have more control in the whole design process, and hopefully just apply it to other contexts where more geometric control is needed, for example, for data augmentation. If usually the problem with medical data is the fact that we are kind of limited in terms of available data, and we would like to do a data augmentation process which is consistent and relevant in that context in order to be able to apply some machine learning techniques on it and train using that data. So one possible way to apply these kind of techniques is to indeed, given some samples, for example, in the context of histological data, and inject some control, geometry control through that. For example, say that I would like to have similar patterns, similar textures, where the proportion of each of these colors, for example, in the histological case, that would be very specific colors that we need. And we ask the system to generate that kind of data that would be consistent, at least in terms of the proportion of colors that we need, in order to see how we can train on this data. So this is something that we can mention as very concrete and tangible application of this setting, and I think I can somehow conclude on this part saying that, okay, we try to cover, at least to present some link between circle packing in the context of discrete conformal mapping to weighted triangulations, and we could showcase some of the applications in different areas using this methodology. Before I finish, if there is no questions, this time I was more on time based on what I wanted to say, because I had to remove a good part of it linked to machine learning techniques. These are the set of references that are linked to what I've presented today. And I would like to finish with this final remark, because in this conference I was supposed to somehow represent the computer graphics community, and I would have a very brief, but to my sense important message to deliver, because, for example, during the presentation of Scikit Shapes Library, Jean mentioned the fact that, okay, each of these categories of scientific fields, computer graphics was somehow mentioned as with some highlight on virtual reality and video games. I wanted to say that personally, at least as a part of this community, I think geometric processing in this community means much more to me. Mainly, I'm not particularly promoting like VR or video games that are highly based on what we do indeed in our community. I'm more on the, let's say, visual computing part, where we can deliver indeed some messages through this visual channel, if you want, and visual techniques that we are developing. And as an example, I wanted to say you that I was really delighted to see yesterday to receive a message from my son, just sharing one of his designs with Lego, so real, actual, not virtual game. sorting coins. By the way, since it was a kind of circle pattern, based on the radii of these coins, he's trying to really sort them. I always try to promote like our geometric intuition or modeling kind of geometric thinking to this educational approaches. And I think these are inspiring really creative applicative scenarios, like in fabrication. We have many examples, and we have many colleagues who are dedicated to this kind of applications. And for me, geometric-driven visual computer things could bring really creativity and could be seen as visual language, if you want, to transfer knowledge differently. So this is what I really dream of. That's one day when we present also computer graphics, we put some accent on the educational part of it. I would like to really contribute in that sense and bring a new vision to our next generation. I thank you for your attention. Thank you.